Alright everyone, welcome back to the Binary Tree Machine Learning AI course. This is week 2 linear regression. As we discussed last time, we talked about different types of variables and briefly looked at the correlation coefficient, which is a huge part of linear regression. So let's go ahead and take a chance to look at this example of linear regression. This is showing a graph of a student's Algebra 1 test score versus a math assessment score. So the math assessment score versus the percent of school days attended. So we're showing on the y-axis the score that they got on their math test, and then on the x-axis the percent of school days that they actually attended. We think, while looking at this, let's remember this is a 2D, like a two variable scatter plot, as we said, to show two quantitative data points, meaning the percent of school days attended and the Algebra 1 score. So we're thinking here that attendance is predicting test score. That's our idea. So we've made a scatter plot to show that attendance is linearly related to test score. So as attendance increases, we can kind of see, as attendance increases, that Algebra 1 score is also increasing. The test score is increasing. We can see that line that's going upwards in a positive trend. Now, if we remember, with the correlation coefficient, that's something that we discussed last time. We discussed that R value, the correlation coefficient, that says how related two things are. So let's look at this. Let's look at this one line here. Y equals mx plus b. This is the classic formula for a line. Y equals mx plus b is quite literally just a line in a plane where m is the slope and b is the y-intercept. Everyone has learned this at some point if you've done algebra. Now, let's look at this, right? This is just a line as an example. We have y equals 2x plus 1. This is the same thing as y equals mx plus b. So basically here, 2 is the slope and 1 is the y-intercept. So right here, 1 is the y-intercept. And then the slope, m, is how fast it increases, which is like the rise over run. So it means it goes up 2 for every 1 across. This is the math behind what we're doing. Exactly, so up 2 over 1. Slope is 2. Y-intercept is the height intercept where it goes across the y-axis. Now, let's relate the algebra to the statistics. This is our old algebra equation that we know. We all know this, we love this. But now we need to look over at stats. Stats is what we're really looking at because that's the whole fundamental idea behind AI and machine learning. So here, our linear regression is very similar, okay? It looks pretty similar, right? The slope is the same. Instead, it's B1 or beta 1, as that symbol is beta. So slope and beta 1. There's a y-intercept, which is beta naught and b. And then there's one little thing, e. That is the error. That is the residual. So, to summarize, y equals beta naught plus beta 1 plus error, e. That is what our linear regression equivalent to linear equations are within statistics. So, as we see this, let's look at an example of exactly how that would look. So, we have done a linear regression on our data that we showed earlier of the Texas student score, a math score, versus the percent of school days attended. Right here, we see that it's an upwards trend and there's a y-intercept somewhere and then there's error, and exactly the equation here that defines it is shown. Negative 7.69 plus 0.57x plus e, the error. So B naught is negative 7.69, and B1, or beta, I'm saying B, but it's beta, should be 0.57. So what this means is basically the same thing as what a linear equation would mean, right? So here, what that beta 1 shows is for every 1 unit increase in days attended, we predict that a student's test score will rise by 0.57 points. It's the same thing as a linear equation, but now we're talking about it in terms of regression. Now, let's look at this. So if a student attends 87% of school days, what is their predicted test score? So we're saying that this is the equation. Let's ignore the error for a second, but looking at this being the equation, what is their predicted test score? Well, we treat it just like a linear equation, and we say, okay, if it's 87%, we plug in 87% for x, and then get what the y response is. So if we plug that in, we get 41.9 as our output, and that's what the prediction is. So if someone attends 87% of school days, their predicted score is a 49. That's not what their actual score necessarily will be, but that's what they predict. Great. This is our first case of machine learning. We actually taught a machine how to predict a student's exam score given their attendance. We made a model, and now if we plug anything into that model, it can predict what a student's exam score might be given their attendance. And it's possibly a really good prediction. So, will our predictions always be perfect? Let's ask that, because I've been saying this whole time, are our predictions perfect or not? Because real data always has problems with it. Real data is not necessarily going to be exactly there. So if I say maybe the student who attended 41% actually was around here, or maybe they were down here, we don't know for sure because real data has any random kind of error. Maybe that one student was super smart. Maybe that one student was not super smart. Anything else, not just the model. The model does not affect our outcome, but there's so many factors to it. So here is where we talk about the residual. So on the screen here, you can see errors or residuals, which was that E that we talked about before being existed here. So if we have predictions, the line is what our predictions are. And then these actual values are the dots, right? So there's always a separation between the dots and the errors, or the dots and the actual line, and that's called our error. And when we're doing these models, we're trying to minimize the amount of error that there is, because that should ideally be the least, as it should be the best model when we fit it to having the smallest error. So let's look at these two models. We have model A here and model B here. Model A, model B. Looking at both of them together, which one fits better, do we think? Well, what we do is we kind of estimate based upon how it looks. We kind of eyeball it, right? We eyeball and see, okay, there's this much distance, this much distance, this much distance, this much, and this much. In model A versus model B has this much, this much, this much, this much, and this much. And we have to kind of come up with a metric for which one seems like it has closer errors, like less distance between the line and the points. It seems like model A here is the winner because it has a bit less distance and separation between the points and the line. So perhaps we can call that one a better model. We should actually be quantifying it by like actually taking, instead of eyeballing it, we take the actual measurements and calculate those residuals that we said. The errors or residuals are the actual point versus the predicted. So we take the point that it's at up here or up there and then subtract the line value, which is the predicted. And then when we get that, we see what the residual is. And as we can see, at some points actually, the prediction for B is better. So like at this point it's better and it's worse for A. But in a different one, like right here, it's worse for B and better for A. Now, the first thought that everyone should be having, which I kind of also mentioned earlier, is that the best fit of the line, the best fit is the one that minimizes the residuals, right? So what we should really have is be summing up the residuals and seeing, oh wow, this one has a sum of 0. That means it's a good fit. Here, the sum of the residuals is also 0. Wait a minute. Does that mean it's a good fit? It doesn't look like a good fit. Well, that's where squaring comes in. We have another important concept, which is that we have to square each value that we get. So what that means is we take each of our residuals and then we square them and then sum them up. Because then all of a sudden we see, oh no, the sum of the squared residuals is 8, which means this is not a good fit. But here, the sum of the squared residuals is 0, which means it is a good fit. So what this brings in is the biggest concept right now, is the least squares regression line, LSRL. The LSRL is the least squares regression line, also called the line of best fit. It is the specific line that minimizes the sum of squared residuals across all data points out of every possible line you could draw. So let's say we draw a bunch of lines up through some points. The one that is the best is the one that minimizes the sum of the squares of the residuals between the data and the model. So our regression function here, this is our actual regression line, this minimizes the loss function. Or this minimizes the loss, right? This is a loss function which models how much error we have within our line. So what this part, this whole thing here is showing, what this part represents is the predicted minus actual squared. That's showing us that error, squaring it, and then this sigma function is summing it, and then this is the divisor. So walking through this whole thing, this is getting the mean squared error, MSE. Mean squared error is the average of the squares, or average of the sum of the squares of the residuals. And that's the function we're trying to minimize. Now, this is kind of breaking down everything. Now, this is good. So what's the main goal of machine learning now? So we know we have this least squares regression line, LSRL, but what are we trying to do with machine learning? The whole goal of machine learning is fitting the existing data well, but then predicting accurately on new data the model has never seen before. So this is where test train split comes in. So what we have to do here is we only train our model on a certain chunk of the data. So the training set is the portion of data that you use to fit or build up the model. The model sees this data and learns from it. So basically, we would take maybe, let's say 80% of our points and use those to create the least squares regression line. And then there's a testing set, let's say 20%. We use it to predict the rest of the models, use it to test the model and predict how well, or see how well it's predicting the testing data. And this test set is what you hold back from the model and never let it see during training. You only show it when it's already done making a fit of a line, for example. So the MSE on the testing set is what you'd expect to see on truly new data. The training set is just there to fit the model. The testing set is there for the new data that we're trying to see how well the model is performing. So we'd fit our model on the trained data right here. Let's say we took 80%. I don't know how much percent this is, but we took some percentage of it and then predict on the test data. These are the actual points that we're going to test. And we randomly split this up. a normal splitting is usually 80-20, 80% training, 20% testing. You can change that up, but that's like a regular kind of split that people have. So on the test, the MSE is 16.23. So on average, the square error, the residuals, was 16.23. And that kind of gives us an idea of how well the model would actually do on new data once we feed it new data. So the goal wasn't just to predict the exact score, but it was to find a line that generally describes how attendance relates to test scores. So generally, this line will show that, okay, if a student attends more school, they'll generally be getting a better score on their test. That's pretty clear to see. So if like someone spent only 70% of days in school versus 100, there should be a clear difference. Now, what are some other variables besides attendance that might help predict a student's score, right? There are going to be other things, as I said. It's not just based on attendance. Maybe it's based on real intelligence. Maybe it's based on age level. Maybe how much food they ate in the morning before the test. There's so many different variables that could kind of cause these differences. This is where multiple regression comes in. Let's say the teacher. Let's say the teacher is the reason that the student's test score is different. It's very possible. So we already did a regression on, we already did a simple regression on just attendance rate and test scores. Okay, we've got that. Now what we can introduce is the multiple regression using teachers. So what we've done here is we've introduced a new line. We've added a teacher as a second predictor, and we now have a different model that says, okay, maybe based on teacher A versus teacher B, they have different test scores. And in this case, yes, it is different. We see that teacher B is scoring lower than teacher A at a given score. So if we now try and predict based on the fact of which teacher they have, the MSE, the error, gets lowered to 16.2 because these different lines represent the different teacher predictions. Isn't that amazing? So the added effect of having teacher A, which is this beta 2 variable, this tells us that if they have teacher A, then they're going to get some kind of bump in their score for each score. Now, multiple regression can include many variables, right? We can include as many variables as we want. We can say attendance, teachers, school, test score last year. We can say how much food they ate, how old they are, like anything we think may affect it, we could add it. But including a lot of variables can get hard to visualize, and eventually, adding too many dimensions can add some confusion and maybe overfit, which is stuff we'll talk about later. But for now, this is something to keep in mind.